Hello, I'm Tom Buchholz. Thank you for viewing this video, Patterns for Elementary Particles, Dark Matter, Dark Energy, and Properties of Objects. This slide notes a physics challenge. People say that more than 5/6 of the matter in many galaxies might be dark matter. But what is dark matter? This slide denotes a physics challenge. People say that dark energy might drive the so-called dark energy accelerated expansion of the universe. But what is dark energy? This presentation features 5 topics and related challenges that associate with unexplained patterns in physics. One topic is the properties of objects. The challenge is to catalog properties such as charge and intrinsic angular momentum of objects. Regarding elementary particles, the challenge is to catalog all known elementary particles and predict new elementary particles. Regarding dark matter, can one specify dark matter and thereby explain ratios of not ordinary matter effects to ordinary matter effects? Can one explain data that associate with gravity and so-called dark energy phenomena? Can one catalog conservation laws? Each one of the challenges is at least 80 years old. You might ask, why now? There might be enough data about dark matter and about gravity plus dark energy to assess the validity of models. The chart shows measured ratios of not ordinary matter effects to ordinary matter effects. The ratios are approximately ratios of integers. Maybe one can assess the usefulness of various models. Maybe one can anticipate useful models. For example, popular modeling suggests that, long ago, atomic transitions produced 1/2 of today's cosmic optical background radiation. Perhaps another set of atom-like objects produced the other half. This talk discusses so-called new modeling, which, when put together with successful popular modeling, seems to address the challenges. This talk outlines models and results that seem to comport with data. This talk does not cover all the details. You can replay the video to look at details that the slides show, and you can look at more detailed discussions such as the ones to which this slide alludes. New modeling focuses on interactions between an object O, with O as in observer, and an object I, with I as in inferred by the observer object. New modeling features an adaptation of popular physics multipole expansions that associate with potentials and with properties that object O infers regarding object I. For example, for electromagnetism, a monopole potential can associate with the property of charge. Dipole can associate with charge current and with magnetic moment. In new modeling for gravity, monopole can associate with energy, and dipole can associate with momentum and angular momentum. New modeling assumes that nature includes 6 isomers, or near copies, of most elementary particles. Perhaps amazingly, new modeling uses integer arithmetic equations to discuss and extrapolate based on popular modeling notions of multipole expansions. This slide features notions about integer arithmetic equations. Each equation is of the form S equals the sum of some terms. Each term has the form k times S sub k. The k's are positive integers. Each k can appear only once in a sum. Each S sub k can be +1 or -1. Sigma denotes the absolute value of a sum. Capital K denotes the set of positive integers that contribute to the sum. N sub k is the number of integers. Solutions come in so-called solution pairs. For a solution pair, one solution is the negative of the other solution. Sigma equals 1 associates with the popular modeling notion that electromagnetism associates with spin 1. Sigma equals 2 associates with spin 2 and with gravity. N sub k equals 1 links to monopole. N sub k equals 2 links to dipole, and so forth. Positive sums link to left circular polarization for the respective field. Negative sums link to right circular polarization. For sigma equals 0, some solution pairs associate with families of elementary particles. Some sigma equals 0 solution pairs associate with spin states for two-component systems, such as atoms, for which one component is the cloud of electrons and the other component is the atomic nucleus. This chart provides a possible analog for elementary particles to the periodic table for chemical elements. Each so-called family associates with 1, or in the case of quarks, 2, solution pairs. The chart points to all known elementary particles. The chart points to a possible inflaton, which some cosmology anticipates, and a possible graviton. The chart also points to a would-be J boson, which would associate with the Pauli exclusion principle. New modeling suggests patterns that associate with elementary particles. N sub k links closely to the capital S, the spin in units of h-bar. Each solution pair has a 1 and a 3 in its set capital K. The integers 4, 6, and 8 link to binary choices, such as for 6, fermions or bosons. New modeling suggests that there are 6 isomers of most elementary particles. Across the isomers, the counterpart elementary particles have the same mass. Isomers differ with respect to the handedness of elementary particles and with respect to the match for leptons between flavor and mass. Stuff based on isomer 3 evolves similarly to ordinary matter, or isomer 0 stuff. Stuff based on the other 4 isomers evolves differently. The upper part of the chart does not show the photon or the would-be graviton. The would-be graviton's monopole component, which associates with energy, interacts equally with all 6 isomers. In contrast, people do not see much about dark matter. New modeling suggests that each of the isomers has its own instance of charge and does not sense most of the electromagnetism that associates with the other 5 isomers. Across the various components of gravity and electromagnetism, some properties associate with one instance and with that instance having an interaction reach of 6 isomers. Some properties associate with 3 instances for which each instance has an interaction reach of 2 isomers, and some properties associate with 6 instances for which each instance has an interaction reach of 1 isomer. This chart suggests that new modeling plus popular modeling explains ratios of dark matter effects to ordinary matter effects. The chart features a notion of timelines, with earlier to the left preceding later to the right. Smaller objects transit timelines earlier and more quickly than do larger objects, as would be consistent with the notions that multipole expansions pertain and that large things generally move apart from each other. The notions that dipole and octopole gravity associate with repulsion extrapolate from popular modeling notions of Lorentz invariance for electromagnetism. For the forming of solar systems, the dominant component of gravity is an attracting quadrupole component that has a reach of 1 isomer. Some solar systems form as essentially all ordinary matter. Some solar systems form as essentially all 1 isomer of dark matter. Galaxies evolve more slowly. Galaxies form, often based on 1 isomer halos. Some of these halos were essentially all ordinary matter. Some were essentially all dark matter. Over time, the dominant isomer can repel, based on dipole repulsion, one other isomer. When monopole gravity takes over, some galaxies evolve based on attracting stuff from around themselves. These galaxies can have about 4 times as much dark matter as ordinary matter. Many galaxies that we see today result from multiple mergers. Such mergers tend to result in the ratio of 5 plus dark matter to 1 ordinary matter. Galaxy clusters can exhibit the same ratio as does the observable universe. The plus in 5 plus to 1 might result from asymmetric transfers of energy between isomers because 4 isomers evolve differently than do isomers 0 and 3, and because electromagnetism has reached 6 components. Regarding the observable universe, data exists regarding 2 eras, a multi-billion years era in which the so-called rate of expansion decreases, and a multi-billion years era in which the rate of expansion increases. New modeling is compatible with the notion of an inflationary epoch, which would link to octopole repelling components of gravity. People suggest that popular modeling underestimates recent era increases in the rate of expansion. If one uses an equation of state that adequately describes nature during the early part of the attracting multi-billion years era, and if one tries to extrapolate that equation of state to the repelling, or more recent, multi-billion years era, new modeling suggests, based in part on a reach of 1 for quadrupole and a reach of 2 for dipole, that popular modeling would significantly underestimate a component of repulsion. New modeling offers at least a part of a possible solution regarding current so-called tensions regarding the cosmology of large-scale objects. The other 2 ratios that this chart shows reflect amounts of light and do not necessarily associate with the eras with the attracting and repelling components of gravity. Cosmic electromagnetic background radiation formed early in the attracting era. People observe today twice as much optical background as popular modeling anticipates. Similarly, popular modeling for hydrogen atom hyperfine interactions suggests only half as much depletion of cosmic microwave background radiation as people observe. New modeling suggests that each of the 2 missing factors of 2 associates with isomer 3 atom-like objects. This slide reintroduces the topic of properties of objects and the topic of conservation laws. The first 3 columns in this chart feature aspects of new modeling: solution pairs, numbers of instances, and reaches. The 4th column features properties of objects and fields. The remaining columns associate with popular physics notions. Based on notions to which this chart alludes, new modeling seems to provide cataloging and insight regarding properties, including charge, energy, surface temperature, and atomic state, states, including elementary particles and, for elementary bosons, allowed decays, components of electromagnetic and gravitational fields, spin states of 2-component objects, and popular modeling notions of gauge symmetries. This talk does not cover some results that associate with new modeling. For example, relationships between values of properties for elementary particles, a relationship between the strength of electromagnetism and the strength of gravity, and suggested masses for at least 2 neutrinos. This chart contrasts and unites aspects of popular modeling and new modeling. For each of the first 5 aspects, generally popular modeling inputs the list based on inferences that people make from data. A goal, seemingly now partly realized for new modeling, is that new modeling outputs such lists. Other goals for new modeling include that new modeling comports with nature and that new modeling synergizes with successful popular modeling. In summary, new modeling seems to help regarding the 5 topics and the 5 challenges. Thank you for viewing this presentation.